Okay, hi everyone. My name is Margaret Ikape. I am a graduate student at the University of Toronto, and I'm very excited for this opportunity to share my work with all of you. My talk today is broadly about constraining reionization parameters, and this is work done in collaboration with all these wonderful people I have listed here. Okay, I'd like to begin my talk with this slide here. This slide shows the history of the universe from the Big Bang on the right to the present epoch on the left. The region I've highlighted in blue, in the blue box here, shows the phase, the era of the universe that I'm particularly excited about. This is the Epoch of Reionization. Okay, so after the Dark Ages, gravitational attraction operated on very slight overdensities in the matter distribution, resulting in the first stars. And these stars are believed to cause the transition from a neutral universe to an ionized universe. So much is still very unknown about this epoch. Fortunately, this situation is set to change with the advent of powerful new telescope facilities that are coming up in the near future. Some of the open questions surrounding this epoch I've listed them here. They include: when did reionization start? How long did it last? And many more questions that are exciting. Okay, so peering into this reionization epoch has been both a challenge and a quest for astronomers all over the world. For this work, we will be probing this reionization epoch using the cosmic microwave background radiation, the CMB. And the way we get information from the CMB is through the Sunyaev Zel'dovich effect. In particular, we use the kinematic Sunyaev Zel'dovich effect, the KZ. I'll call the KZ from now on. So we use this effect to constrain measurements of the optical depth tau and thereby resolve parameter degeneracies between tau and other cosmological parameters. Okay, so the KZ effect is a Doppler boosting of CMB photons as the Compton scatter of free electrons moving with a non-zero velocity along the line of sight, as shown in this image. On the left, the CMB temperature fluctuation that is caused by this effect is given by this expression shown here below. T is just the mean CMB temperature. Delta T is the cross section. Chi here is the co-moving distance, which is a function of redshift. Ne is the physical number density of free electrons. Tau, which is very important to us in this work, is the optical depth. The optical depth is a very small number, so this exponential is mostly set to 1. The vector VE is the peculiar velocity of the free electrons, and n hat here is the direction defined from the observer to the source. Okay, so the KZ effect, this KZ effect usually comes in two varieties. We have the late time KZ effect, which is around redshifts less than 3, and it comes from moving electrons in galaxy clusters. And then we have this early time KZ effect at redshift of around 7. This early time KZ effect it gives us information about reionization, and so that's this effect, the early time effect, is most important to us in this work, and we disregard the late time effect, which really is what's shown in this diagram on the left. Okay, the simulation used in this work to study the shape and the amplitude of the KZ signal is detailed in this paper here by Marcelo Alvarez. Our simulation has as input 3 fundamental physical parameters that control the morphology and the history of reionization. And they include the ionization efficiency, the main free path of the ionizing photons, and the minimum mass of halos hosting these ionizing sources. So the reionization history for each of the simulation on the grid is used to determine the optical depth parameter tau and the duration of reionization delta z. Okay, so here I am just going to show a quick movie that's created by running this simulation by Marcelo Alvarez. And it shows the gradual reionization of a typical patch of the universe. So the blue bubbles you see here are the hot ionized regions in the early universe that continue to grow and eventually overlap until the whole universe becomes ionized. So the field of view of this box is about 200 million light years, and the calculation shows the first billion years of the universe. This simulation creates initial linear density fields from initial conditions and uses the excursion set algorithm to generate reionization fields. Okay. So we consider 2 statistical probes of the reionization KZ signal. First, we consider the angular power spectrum, which is the 2-point function, and the 4-point function as described in this paper, Ferraro and Smith, 2018. The derivative of the power spectrum with respect to these model parameters we used in our Fisher forecast are obtained by just running a series of the simulations with different parameters, and together with the mapping from physical parameters to tau and delta z, we use this for both the 2-point and the 4-point functions, the 2-point and the 4-point Fisher forecast. The fiducial model values we adopt in this work are shown here. We have M min, zeta, and lambda, and this corresponds to tau value of 0.06 and delta z of around 1.2. Okay, so we discover here that the parameters M min and zeta are the most closely related to the empirical parameters we consider in this work, as seen from these figures. From particularly this one on the lower right, we see that the amplitude and the shape of the KZ signal changes very little when we vary the mean free path. So for this work, we decided to fix lambda and vary the other two parameters. Okay. Here I show the dependence of the KZ power spectrum on reionization model parameters. The shaded bars show the 1 sigma uncertainties on the power spectrum for a combination of CMB-S4 and Planck data. So CMB-S4 is a next generation CMB experiment that is set to go online sometime in 2027. Okay. The solid and the dotted lines show a variation of input model parameters M min and zeta on the left, and the resulting reionization history parameters tau and delta z on the right. And we see that the spectral shape between multiples of 2000 and 8000 is accessible to us given improved sensitivities. And here I show the response of the KZ power spectrum to variation in tau and delta z. And we see that increasing either tau or delta z results in more power at multiples greater than 1,000. And for the final result we have for now, we show the individual and the joint constraints on delta z and tau from the KZ 2-point and the 4-point function. So we see that the 2-point function shown in pink here weakly constrains the optical depth, but tightly constrains the duration of reionization. Conversely, the 4-point function is more sensitive to the optical depth. So the 4-point function in blue is more sensitive to the optical depth than to the duration of reionization. And when combined together, as shown in the black ellipse, and also adding in the Planck primary CMB constraints on tau, we get that the joint forecast yields sigma of tau as 0.003 and a sigma of delta z as 0.25. So we see that the complementary degeneracy directions of the 2-point function and the 4-point functions effectively breaks the degeneracy between these reionization parameters. And we can really explain these different degeneracy directions like this. So while you change a parameter such as the duration of reionization, this would change the power spectrum, but it will also change the amount of non-Gaussianity in a very different way. So for example, a shorter reionization epoch would lead to a more non-Gaussian KZ field and enhance the 4-point function compared to the 2-point function. And so by measuring both of this, we can effectively break the parameter degeneracy and obtain tighter limits on reionization. Okay, so for my conclusions, I've illustrated that we can combine the 4-point and the 2-point constraints to break degeneracies to break degeneracies between parameters of reionization, and we did that and forecast sigma of tau as 0.003 and sigma of delta z as 0.25 for using a combination of CMBS4, an upcoming CMB experiment, and the Planck data. Thank you very much.